Hello everyone, I am Mohammad Sarmad Mir, working as an early stage researcher in Marie Curie ITN project ENLIGHTEM. Today I am presenting you paper with title LED to LED based VLC systems, developments and open problems. The work is contributed by myself, Borja Genoves and Domenico Giustiniano from IMDEA Network Spain, and Behnaz Majlesein and Julio Rufo from LightBee. Visible light communication combines illumination with data transmission. VLC aims to retrofit the existing lighting infrastructure for high-speed and power-efficient data communication. Nowadays, LEDs are commonly used for generalized lighting applications. The good thing is the LEDs can be modulated at a very high speed that make it an ideal choice for visible light communication. VLC can be an enabling technology for the vast deployment of IoT devices. IoT are the devices which are interconnected and they exchange data over a wireless link. There has been an exponential growth in IoT devices worldwide. It is estimated that by 2025, more than 25 billion IoT devices will be installed worldwide. With this vast deployment, a lot of challenges in terms of technology appears. For example, for the energy efficient connectivity and for the data handling. There are mainly two components of VLC system. One is the VLC transmitter, which is a light source which can be modulated, and the other is the VLC receiver, which can be a photodiode, solar cell, image sensor, or an LED. LEDs are well known to emit light. However, another key feature of LED that is not fully explored is the use of LED as a photo receiver. There are many advantages of using LED as they are sensitive to a much lower band of wavelengths. Uh, if in contrast you want to use a photodiode, you need very expensive filters to get the narrow band of wavelengths. LEDs are more robust to outdoor scenarios than photodiode, for example, in sunlight. The LED sensitivity is very stable over time, and LEDs can be set up as a both transmitter and receiver, which enables a bidirectional link using only a single LED at each end. LEDs are widely available around us compared to photodiodes. So the question is, can LED to LED communication can enable the vast deployment of IoT devices? If we go to fundamentals, LED can be used as a transmitter. For example, if we put a forward bias to LED, it generates electrons, and the electrons and holes recombine, and consequently they emit light. And if we are using LED as a receiver and we incident the LED with the photons with energy greater than the band gap of the material used in LEDs, it creates the electrons and holes, and a weak electric field in the depletion region causes the flow of electrons and holes, which produce a tiny flow of current, photo current. And you can see with the equation one that this photocurrent is directly proportional to the spectral irradiance and the responsivity and the area of photosensitive device. So more the light, more the optical flux, more will be the current generated. So if we go to the history, in 1962, first visible light LED was produced, and from that time there is a gradual development by producing LEDs of different colors and different power. In 1990s, it was explored the use of LED as a wavelength selected photo detector. You can see in the figure that Miyazaki et al. They used different combinations from RGB LEDs, blue to red, blue to green, and they compared the performance of all the combinations. They found that red to red LED gives the maximum range. They achieved the data rate of 100 kb per second up to range of 55 centimeter using red LED at both ends. They extended their work to transmit a TV signal at 6 megahertz, but with a very short range. Then researchers proposed LED to LED communication based on charging and discharging time of LEDs. Of LEDs, of the internal parasitic capacitance of LED. So you can see in the figure that when they are using just a single microcontroller as an emitter, the LED is forward biased. And then as in the receiver phase, the first it is reverse biased to charge the internal capacitance of LED. And then it is exposed, and then they measure the time to discharge. When there is low light, which can be bit zero, the higher is the time to discharge. And when there is a presence of light, it is bit one, and the time of discharge of capacitor is less. By comparing the discharge time, they decide between the bit 0 and 1. Then there are some works which are based on the higher level protocols. Authors of 6 explored the network architecture with software-based physical and medium access control layer using very low-cost microcontrollers and LEDs. They claimed in 6 they claimed to achieve the data rate of 870 bit per second with a range of about 2 meters. Another work was presented in 7 by Wang et al., which they produce a very reliable VLC link in the network scenario. They used open VLC boards, which are currently available for research community for research on visible light, and they claimed the data rate of 12 kb per second with a 5-meter range. Another work was presented with the name Real VLC, which is an adaptive VLC receiver. And the receiver dynamically configure itself to maintain the link over different lighting conditions. They used white LED as transmitter and red LED and photodiode in complementary configuration as a receiver. They achieved a data rate of 20 kb per second with 5-meter range. And then there are some work in which the multicolor modulation schemes are explored in 9 bidirectional VLC using OFDM modulation scheme. They achieve, due to multicolor modulation, they achieve high data rates of 155 MB per second for 1-meter link by using red LEDs at both ends. In another work, they use full duplex communication. They achieve full duplex communication using OFDM, and they get the data rate of 49 kb per second with 15-meter range. And they use green LED as transmitter and yellow as receiver. In one work, they claim the data rate of gigabit per second using OFDM, which requires intense processing, as we can see in the figure on the right side. They are using immense processing using DSP kits and ADCs, and they replace on the transmitter side. They replace the LED with the laser diode, and they use 2 yellow LEDs as receiver. By using the laser diode, they achieve a very high data rate. So going into the challenges and research directions, I want to shed some light on different LED characteristics. LEDs are made for illumination as a transmitter. So if you want to use if you want to use it as a receiver, there are many characteristics which are not available in the data sheet. So one of them is the optical spectrum. For example, when you are receiving, the LED is sensitive to certain wavelengths. So you need to measure the spectral response of the LED by exposing it to different wavelengths. The second is field of view, which can be measured by transmitting from different angle of incidence on the LED. to measure the field of view of LED if you want to use it as a receiver. And then there are different effect of temperature on the spectral response of the LED. Even on the transmitter side, there is some variation in the transmission spectrum. And as a receiver side, also the spectral response varies. You can see in the figure that by changing the temperature from 27 degree to 80, there is a significant change in the spectral response. There are multiple challenges we identified in this field, and there are a lot of research potential for everyone who wants to pursue in this field. We can go one by one. The first challenge is that LED has a low responsivity, and they are sensitive to a very narrow wavelength, and there is a variation in spectral response with temperature. So this opens up multiple research directions. One of them is that we can design a multi-LED receiver covering the full range of visible light spectrum by using different color LEDs, for example. And to increase the sensitivity, we can apply a reverse bias to the LED at receiver, which will increase the sensitivity of the LEDs. Another research direction that we observed is that in many designs they ignore the optical front end. So if we have a proper optical front end, some lens to diverge the to converge the light towards the LED, it can enhance the receiver gain without any increase in the power consumption. The third research direction could be to characterize the spectral variations due to the temperature change, and we can have some temperature compensation techniques to compensate on the transmitter or receiver side. The second challenge is how we can harvest energy from the LEDs SLIPT, which is a simultaneous light wave information power transfer system using LEDs. So in last decade, there are some works in which they are using LEDs for harvesting power. If we make them harvest enough power to operate some sensors or some microcontrollers, then it can help us, especially in the IoT applications where we cannot use the cables. And if we go for batteries, they need replacement and add to the pollution. So harvesting energy is the best option. So if we can use LEDs, this can be a very good potential research direction. And then for IoT devices on a mobile device, we have a very limited energy budget. For uplink communication, it is not easy to switch on off the LED for transmission. So to design ultra low power communication for uplink is another good research direction. Now, the third challenge is how to use the high power LEDs and use the energy efficient processing. Normally, in most of the work, they use the off-the-shelf 5 mm small LED for LED to LED communication for small applications, for example, toy to toy. But if you want to use, for example, in indoor environment, in a room, we need large LEDs which can illuminate as well as they can communicate. But with large LEDs, there's a problem of thermal management which need to be solved, and also the capacitance increases which reduce the bandwidth. So these problems need to be solved to use the high power LEDs, which can give us better range of communication and better illumination. Another research direction related to this is low power and energy efficient processing at receiver. For example, in OFDM, we get a higher data rate, but the processing is very intense. So we need to design some low power and energy efficient processing techniques. The last one is that the LEDs has a limited field of view. So in a mobile, in a scenario where the user is moving, and it's not easy to keep the link alive when the user moves from one LED to another, because the LED has a limited field of view. So this is a very good potential research direction to enable seamless coverage in mobile scenarios and reduce the effect of light variations, and this can be done by dynamically adjusting the field of view. So to conclude that we have unified the recent works in the domain of LED to LED communication, and we highlighted some features of LEDs as receiver. We identified the potential challenges and corresponding research directions, and we envision that LED to LED communication can contribute to the massive deployment of VLC for IoT devices. Thank you very much.